Hi folks, this is Dr. Young, and in this video we're going to talk about reductive amination, which is another way to make amines, right? So amination, of course, means to add an amine. So we'll be adding an amine onto a pre-existing molecule. And then reductive is exactly what it sounds like, right? We're also going to do a reduction. And we'll see that this reduction can either be the addition like a hydrogenation, or it can be from adding like a hydride. So we are here, right? So we're getting down here. We've got reductive amination. We're right down here, right? And I'll show you in a sec how we have to start with an aldehyde or ketone, and then we're going to make a primary, secondary, or tertiary amine. So that's what we're going to focus on for this video. Now, like I said, right, what's nice about this one is that it actually can make secondary or tertiary amines, right? That was the big limitation of these, was that they could only make, right, could only make primaries. Only make primary amines. Where if you look down here, right, for this is an example of reductive amination, I can make this no problem, and we have a tertiary amine. And it's well controlled. It's not like it was one of those runaway polyalkylations, like if you try to do just an SN2. But this is a nice clean way to make tertiaries or secondaries, or even a primary if you wanted to. But it's a good reaction that you should definitely know. So how do we spot it, right? One of the big things, like I was saying before, you're always going to start with an aldehyde or ketone, right? So you're always going to have an aldehyde or ketone. In this case, I've written down a ketone. You are also going to have an amine. It can be really any kind of amine that you can add that's a good nucleophile. So I just put not tertiaries, right? Because they don't make great nucleophiles, and that they don't stick. If they do add, they get popped back out. So this would mean things like not, something like not triethylamine, not pyridine. Not any, just no tertiaries. That's basically it. It could be ammonia. It could be a primary or a secondary. So in this case, right, I've got a secondary amine, so that works fine. I'll write that down, secondary amine. And we're going to need some sort of weak acid. You're usually going to find a weak acid in here, right? So good examples would be trifluoroacetic acid, so TFA, trifluoroacetic acid, CF3, with the carbonyl. Sometimes you find things like NaHSO4, right? So the bisulfate. It could be something like acetic acid. Something like that. Acetic acid, right? Which we all know. Acetic acid. So things like that, right? You're probably not going to find like HCl or sulfuric acid or nitric acid, just because they're going to possibly react with your reducing agent, which might be an issue. So they tend to be weak acids if you see them. And in this case, right, I have ACH, which is an abbreviation for acetic acid. Right, your CH3 double bond O, OH. And then the last thing that you're going to need, right, so the reductive aminations have a lot of parts. The last thing you're going to need is some sort of reducing agent. So things like NaBH3CN, or some sort of catalytic hydrogenation thing, oftentimes nickel with H2. In this case, I use the NaBH3CN, which is my reducing agent. Now I'm going to draw, this should look kind of familiar, right? It looks a lot like NaBH4. So I'm just going to draw those and compare them. So here's my BH4, right, versus the BH3, CN. And if you take a look at these, right, the big difference is that instead of a hydrogen, we have a cyano group on one of them, right, on the type of reducing agent that we're going to use for these. And if you look at these, right, we should remember that the CN group is a strong electron withdrawing group. It really pulls electrons out. And what that means is that it stabilizes this anion. It stabilizes the anion, which means, right, that because that boron has less of a negative charge, it is now a weaker hydride donor. It is now a weaker reducing agent. So the NABH3CN is a weaker reducing agent. It's a weaker reducing agent. Let me clean that up a little bit. It's a weaker reducing agent because it has that CN group on to help stabilize it. And there are other reducing agents that are like this that just make the BH4 version weaker. But the main reason why we're adding this weaker one is we're going to see in a second, we're going to have protonated imines or these iminium salts that are really easy to reduce. And what we don't want to do is we don't want to reduce the starting aldehyde or ketone. So what's nice about these is that they are not great, are not good at reducing ketones and aldehydes. So I don't have to worry about them reducing my ketone or aldehyde first. That's the important thing about using them. If I'd used NABH4, then I would have reduced my aldehyde and ketone into an alcohol, and then I'd be dead in the water and this reaction won't occur. And I'll show you the mechanism here in just a second. But anyways, if I have all of these things, right, an aldehyde, a ketone, an amine, an acid, and a reducing agent, that's the reductive amination stuff. So that's what we're going to start looking for here. And what you'll notice is that basically we've replaced the carbonyl, right? If I look on my molecule, I've replaced the carbonyl. So carbon 1, carbon 2, 3, and 4. Carbon 1, 2, 3, and 4. So at that carbon 2 there where the carbonyl was, I now have my nitrogen. And the other new thing I have is a hydrogen that was added from my reducing agent, right? So I did a reduction and an amination, hence the term reductive amination, right? I've added a hydride and I have added a nitrogen to that carbon. I've reduced it. So what does this mechanism look like? Let's go through it. Add my lone pairs to my carbonyl, my lone pairs to my amine. I'm going to draw out my acetic acid here. And the only reason for these weak acids is to help you protonate your carbonyl. They're not great. I mean, this is just a little tiny bit that you're going to form, but it's going to be enough that it's going to help activate that carbonyl towards a nucleophilic attack, right? Because if you remember, right, this should all look very familiar from when we formed imines. And in fact, I guess I should say this now. Well, let me finish drawing this molecule and then I will. Right, so you could have, and I'll just draw this little resonance contributor here. What I should put about this mechanism here is that the mechanism is the formation of an imine, right? You're basically going to do that whole mechanism for the formation of an imine. Then it's just a reduction. Then reduce with NaBH3CN. So this mechanism is going to look very, very, very familiar. So I've protonated my carbonyl, made it a better electrophile. I have my amine, so I've got my diethylamine here. That is now going to go ahead and add into that carbonyl carbon. Nitrogen's now positive, just like we saw with those other reactions, right? The formation of imine. Nitrogen's going to lose that hydrogen, right? It's going to become neutral again. And I'll do this in 2 steps, but you could draw it in 1 if you want to just write proton transfer. So nitrogen's going to take back electrons. We're going to have H available now. That hydrogen could go back on the nitrogen, which is why this is a reversible step, or the alcohol could pick it up, give us something new. And again, that oxygen being positive, it's not very stable being positive, so it wants to take electrons back from something. It could take them back from one of the H's that it's attached to, which is going back a step, or it could leave as water, which is a good leaving group. And that's not so terrible, right? Because we're going to have, and I'm going to start moving down here so I make sure I have enough room for everything. That's pretty stable, right? Because yes, I form a secondary carbocation, but it's going to be resonance stabilized because I have a lone pair on this nitrogen. And so here's just a couple of resonance contributors. All right, so we've got this resonance stabilized cation. Now, it's at this point here, right, if I didn't have a reducing agent around, it's at this point that I would then lose a alpha hydrogen and become an enamine. But since I have this reducing agent around, this NABH3CN, this is where it's going to attack. And I'm kind of running out of room, so I'm going to draw it over here. Here's my BH3CN. And then my Na plus. And so it's at this point that my hydride is going to get spat out and then attack what was that carbonyl carbon to kick electrons back up onto the N and make it neutral. You could have also, if you'd wanted to, it would have been totally fine to have this hydride attack this version instead. Whichever one makes the most sense to you, go for it. But that's going to give you your product, right? Where again, like I said, the hydride that you just added is on here. We're not going to see it because we don't draw CHs, but it's that product right there. So that's the mechanism. Again, it's identical to the imine one that you already know. The only new thing is this last step where you add this reducing agent. I will not ask you the mechanism for if you have H2 and nickel. It's a totally different type of chemistry. We're so not going to worry about it. But I could ask you one involving the sodium hydride with the cyano group on it. So as a possible amine targets, right? Really the only issue that we have to worry about is that we know that the group has to have at least one CH attached to it, right? Because like I just said in that mechanism, you add a hydride to the carbon where the carbonyl was. So you have to have at least a CH group on there. So possible amine targets could be primary, secondary, or tertiary. And at least one group must have a CH at the point of attachment. So I'll say attached to the amine. So if I go through these real quick, this one's primary, that's good. This one's primary, that's fine. Tertiary, fine. Primary, fine. Primary, in theory, fine, right? So again, we can kind of do whatever. But like we said, we need to have at least a CH attached to the amine, which is fine, right? So, whoops. So for this one, I have two hydrogens here, so that works. This one, though, I don't, right? The carbon that's attached to the amine, these are all methyl groups. These are all CH3. So this one I cannot make using reductive amination because I don't, that T-butyl group does not have CH at the point of attachment to the nitrogen. This tertiary one definitely could. I could have done it three ways, right? There's two H's on this, two H's on this, two H's on this. So absolutely, I could have made it from any one of those. Same thing for this one. There's two H's at that point of attachment. But here, right, at this point of attachment, there's no CH. So again, I can't use reductive amination to make that one. And I'll just do two of these to give you ideas of how we would make them from a carbonyl. The idea here is, right, you try to figure out what amine you added. So in this case, I just have NH2, so I must have added ammonia. You pick a reducing agent. I'll pick H2 and nickel this time. You pick an acid. I will pick CF3CO2H, a trifluoroacetic acid. And then you pick your carbonyl compound. And so if I want, right, carbon 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If I wanted that amine at carbon number 1, then that means carbon number 1 is where the carbonyl was. So that means in this case, this must have been an aldehyde. Must have come from that aldehyde. So this aldehyde and those reagents would make that amine. I'll just do one of these other ones here. Let's just say this one. Now this one I could have picked any of these. Let's just say that I wanted to make this 1, 2, 3, that the carbonyl compound. So that means that I had another aldehyde. And that means that all the rest of this, right, if the right-hand side was my aldehyde, this is carbons 1, 2, 3. And the left-hand side is the amine, that means I need to add diethylamine. Right, because that's the piece here, right? I need to add diethylamine. This piece needs to be this piece. And then again, you pick a reducing agent. I'll pick NaBH4CN, and an acid, so I'll pick NaHSO4. And again, the combinations aren't necessarily important for us. And you can do the same thing with that third one. That would be okay, but I'm just not going to because I don't want to make this forever long. So let's take a look at this is a good time for you to pause, get a piece of paper out, do these. I will wait for you for 1 second. So the first 3 are just, fill in the box. And then the last one is a synthesis. No, it's not a synthesis. It's just another fill in the box. So you're just going to want to fill in the box for these. All right, folks, let's go through these. So again, wherever your carbonyl is, 1, 2, 3, 4, that's where you're going to put the nitrogen and you're going to put the hydride. So 1, 2, 3, boom. This carbon's 1, 2, 3, 4. So I know I'm going to put my amine here and an H here. But the problem with this one is that I have a tertiary amine. And so this is not going to work. This is not going to stay, right? Because the tertiary amines can't make that imine or aminium ion. They're just going to add in and they're going to get spat out because they don't have an H on them to lose. And again, if you go back a couple slides and you look at the mechanism, that nitrogen needs to lose at least 1 hydrogen. So it cannot be a tertiary amine. So this is just no reaction. You just say no reaction here. This is not going to work. So I'll do the next one then, 1, 2, just to kind of keep track of things. It looks like I have an aromatic ring. Got a methyl on the left-hand side and a carbon coming off, 1, 2. And it already has 1 hydrogen on here. And I know I'm gonna add 1 from my reducing agent. And then I'm gonna add my amine here, which is this ethyl piece. So I'm just gonna add the N, H, 1, 2, 3 pieces. Yep, 3 pieces. And so if I draw that all without the colors, it's just going to look like this. All right, so I made that amine. I made a secondary amine. Now, if we're working backwards and look at this product, this to me clearly looks like this piece. Right, you got the aniline. And so that means that the carbonyl here must have been right there. That must have been that point of attachment. And so I'm just going to go basically draw that over here. So I have a cyclohexane, and then coming off of it's going to be an aldehyde. If I can draw the aldehyde. There we go. Is going to be the aldehyde. So apparently that aldehyde, that amine, or sodium sulfite or sodium bisulfite, and then the H2 and nickel would give me that product. And I'll erase my little blue carbonyl so that it makes sense again. There we go. And then for this last one, same deal, do some record keeping. This is carbon 1, 2, 3, 4, 5. Carbon 1, 2, 3, 4, 5. Definitely looks like, right, this was reductive amination because at carbon 3 there was a carbonyl. Now there's a nitrogen and a hydride. So you aminated it and you reduced it, which means I need to come up with the list of reagents here. So it looks like this is the amine we're talking about. And I need to add an acid. So let's do the trifluoroacetic acid. And I need a reducing agent. Let's go with the NaBH3CN. And those would be the reagents. You can mix these all together. There are some preps where maybe you might want to make the imine first and then reduced second. If you see that, that's totally fine. But all of these reagents can be mixed together if you don't have any weird functional groups that it's going to interact with. So that's the reductive amination. It's our first way to make different types like secondary and tertiary amines. Really useful strategy. So do some practice. Let me know if you have questions. Happy studying.